Alright, so it's going to be the goal of this video to chat a little bit about how we can use one of these previously constructed no-show tables to slowly start to build up a slightly more conversational narrative that justifies why a particular statement has to be true. So in that last video, we looked at this statement that read, if n is some odd integer, then I know that n squared also has to be an odd integer. And the way that we built this kind of argument up was using one of these little no-show tables. So the first line of this thing kind of gives me my overall hypothesis, which says that n is odd, and then the next kind of subsequent steps all go through this argument leading towards the conclusion, which reads that n squared is odd. And that's a great, fine and dandy little argument. It's kind of clunky in that it's this really big grid. There's a lot of dots that need to be connected. It's not overly friendly for a reader to look at. So what we want to do is we want to transition away from this kind of template kind of grossness into something that's a little bit easier to read. And that's where this notion of a proof is going to come into play. The idea is that if you give me some statement, I want to start to think about how can I actually convince you that this thing is in fact true. And that's all this proof is. It's going to be me as this kind of author. I wrote this statement down and I really want to convince you as the reader that this thing is in fact true. So I'm going to try to represent this thing in a slightly more conversational tone. The idea is that it's kind of like we're having a story together. I'm going to tell you some stuff. You can kind of fill in the dots as you need, but at the end of the day, I really want to be convincing to kind of tell you that this was my assumptions, some things occurred in the middle, and I got down to that conclusion that I claimed I was able to do. I don't really want to leave kind of anything left to the imagination or kind of little holes in my argument. So that's going to be this idea, is that we're going to go from this kind of clunky mess into this slightly nicer to read mess, I guess. It's still kind of a mess, but it's a little bit better. And then at the end of the day, I'm actually going to represent another one of these proofs. The idea is that it's going to be a notion of writing, so you're going to be able to bring in your own little ideas, your own kind of personal pizzazz and writing styles and things like that. There are a few components that need to exist in some of these proofs. Others you can kind of use your own kind of interest and go from there. So in this case, we're still going to be looking at this statement that reads, if n is some odd integer, then if n is some odd integer, then n squared is also going to be an odd integer. And this was this example that we started by looking at a bunch of different examples. I think we tested 1, maybe 3, and 5, and a couple negatives, and we saw that when we squared those things, it kept on kicking out an odd integer. And at that stage, we actually built up this notion of a conjecture. It's this idea that I have a statement that it seems to be true for a bunch of different examples. I haven't found a counterexample yet, and I don't think there's a counterexample, but I don't necessarily know why. And at that stage, that's the notion of a conjecture. It's this idea that I have a statement that I think is true. I haven't broken it yet, but I don't have a formal argument for it. In this case, we're going to be introducing this notion of a theorem, and that's going to be, here's a statement, I'm claiming this thing to be true. Following this thing is actually going to be a proof that justifies why this is true. And what's nice about kind of giving these things various numbers is that later on, you can actually reference some of these previously proven facts. And that's going to be one of these huge components of kind of how math builds on itself. You don't want to constantly keep on reinventing the wheel. Once you know something is true, you can go back, grab that result, and just say, because of this fact that's already been proven by blah, 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 or it was proved by me, or it's found in this textbook, or something like that, you can always go back, reference that thing, and then continue on whatever argument you're saying. If you had to constantly prove everything within your proofs would become huge and horrible and even harder to read in a sense. Okay, so let's dive into some of the kind of structure of what's going on here. So just like that kind of no-show table, we're going to start this thing off with just kind of a big declarative statement about what's all in play. So in this case, we were talking about my hypothesis saying that n has to be odd. Same thing's going to happen here. I'm just going to tell the reader right away that for the rest of this proof, n is going to be some odd integer. And that's exactly what's happening here. I'm assuming n is an odd integer. What's going to happen next is I'm going to play off this notion of, well, how did odd actually influence what's going on? In this case, since n was odd, I knew that there's going to exist some other integer, let's call that thing k, such that n is going to equal 2k plus 1. So that's using that second step. In a sense, we've used this first one and now we've used that second one. So we're at this kind of stage right here in my no-show table. So the idea is that I told the reader that n is going to be odd. Now I'm telling the reader that I'm actually going to be using a little bit more of the structure of what n looks like. I really want to see that n looks like 2k plus 1. And we know that's the big kind of crux of that argument. That little 2 is what makes all of these things work, as well as that little 1 that's off the back of that thing. Now what we're going to do is we're going to let the reader know that there's a whole bunch of algebra about to happen. And that's exactly what happened in our no-show table. There were kind of 3 stages of various algebra of substitution, some algebra, a little bit of factoring, a bunch of that guts went on in there. So I'm just going to let the reader know that there's a little bit of that to come. In this case, you could say by substituting or using algebra or something like that, we obtain blah, the following. In this case, I actually like to represent that little kind of chain of equalities just in the middle of this little paragraph, kind of make it centered so you see it right in the middle, because that's really the big component of this argument. This argument starts by just using the definition of odd. It uses a little bit of algebra in the middle, and then it comes back around to actually using this definition of odd to kind of clean things up at the very end. But the big algebra component is all going to occur in the middle, so you might as well make that kind of its own little chunk. So now I'm just going to do the substitution followed by the expansion via FOIL, and then I'm going to factor out that little 2. And now I'm at the stage that this thing does in fact look like this 2 times something plus 1. Now it's up to me as this kind of author of this proof to convince you that this thing actually is an odd number. And I know this notion of an odd number is going to look like 2 times something plus 1, where that something does have to actually be a nice integer. We know what happens if I don't make that assumption of that thing being an integer. Then you have all of these kind of crazy, weird counterexamples. That one that I kind of always allude to is this idea that you could write 4 actually as a nice little odd number if you didn't check this notion of being an integer as that kind of extra factor. It's this idea that 4 could look like 3 plus 1, and then I could factor a 2 out of that 3 by writing that thing as a 3 halves, and you end up with this 1. So you're like, oh, this thing looks like 2 times L plus 1. In that case, 4 is going to be odd. But we know that that's completely garbage because that 3 halves is not an integer. So I do need to kind of let the reader know that this thing that I'm going to see in the middle of this argument is in fact an integer. And the reason why it's going to be an integer is going to be using this fact that these integers are actually nice underneath a bunch of different properties, in particular underneath addition and multiplication. That's actually all that's existing in the middle of this thing, is that I'm starting off with some integer k. Well, if I square that k, it's still going to be an integer. Multiplying by 2 is going to keep it as an integer. Over here, this multiplication by 2 is going to keep an integer. So I know that this entire expression is still going to be an element of these integers, and everything is good. So that's what's happening in this case, is I'm going to say, since k is some integer, and I know these integers are closed underneath addition and multiplication, we actually can conclude that 2k squared plus 2k is an integer. And now I'm at the stage that, hey, n squared does in fact look like 2l plus 1 for some integer. That's this definition of being odd. And I'm just going to go ahead and tell you what that l has to be. Namely, for this particular choice of l, which reads 2k squared plus 2k. And then at the very end, I'm going to wrap this thing by saying, thus, n squared is an odd integer by definition. If you wanted to, you could say by the definition of odd or something like that. So in this case, what's all happening here is I'm going to try to transition from that expression into this expression, which is the definition of being odd. So this is the somewhat kind of textbooky version of this proof. There's a lot of kind of unnecessary fluff that gets added to it, but it's a really good example to start with. The idea is that when you first start writing proofs, you want to be more formal than you probably feel like you should have to be. Often students get kind of in a trap that they try to skip certain stages, and they might actually be skipping out really, really important steps. Once you start getting a little bit more comfortable with these things, you can start to add in your own writing style, your own pizzazz, and a little bit of your own language as well. So in this case, I actually have another version of this proof, and this is probably actually how I would represent this thing. I'm sometimes less formal in this whole like by the kind of da-da-da-da-da-da stuff. I like to say, I'm like, all right, it's enough that the reader can know that k was an integer to start with, so that thing in there is still going to be an integer. Kind of constantly having to re-say by the closure, blah, 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 becomes a bit exhausting. So in this case, the second version of this proof is going to have a lot of the same structure that last one did, but a few other kind of slight shortenings. So in this case, I'm still going to tell the reader right away that n is going to be an odd integer. Then I'm going to use this idea that because n was odd, I'm really relying on this fact that n has this alternative representation. So n is going to look like 2k plus 1. In that case, I'm still going to enter into this algebra world. I'm actually using this expression that says expanding because that's exactly what I did. I stuffed in 2k plus 1 into n squared. I expanded that thing out and then I recollected afterwards. But the big kind of idea was that I had to get to that stage and then I just cleaned things up a little bit. So in this case, I can enter this world kind of telling the reader, hey, there's a bunch of algebra that's coming up by saying I'm about to expand n squared. Now you know what the operation is going to be. Kind of hope you can come along for the ride and kind of see all those steps occur. Because that's really exactly what these two things are indicating. It's telling the reader, hey, there's a bunch of algebra that's about to happen. You should double check to make sure that I'm actually doing it correctly, but you're going to see a bunch of algebra actually occur. So in this case, doing all of that stuff, I'm leaving myself at the exact same endpoint that one was at, and now I'm going to shorten this up a little bit. I'm just simply going to say, since 2k squared plus 2k is an integer, then I know that it follows from the definition of odd that n squared must be an odd integer. So that is a slightly easier way to see that last chunk. It's a little less wordy. It's not as kind of formal and things like that. It's still formal, but not as kind of obnoxiously formal as that previous example was. All right, so I think we're going to try to dive into another statement afterwards. So I'm going to do the same type of idea. We're going to first build up this kind of no-show table, and then I'll come back to actually showing a different version to write that thing up. So you kind of see that process one or two more times.